So we're going to talk about calorimetry here, and calorimetry is basically experimental way we can measure the heat content of particular chemicals or particular foods or whatever. But before we get to that, let's have a look at specific heat capacity, because this can help us to work out that the amount of energy something has. So first off, when we calculate the energy, when we're using this approach, we need the mass of the water, we need the specific heat capacity of the water in this case, because we're looking at water, and the temperature increase. So it's Q for energy, M for mass of water, not the food, and that's going to be in grams. We've got the C, which is a constant, that's 4.18 joules per gram per degree increase in temperature. So that's what that means. It means if we're putting energy into the system, like as in thing, if I'm going to heat 1 gram of water by 1 degree, it's going to take 4.18 joules. That's what that means. The delta T is a change in temperature. So a simple calculation here is we've got 100 grams of water and it increases by 10 degrees. So our energy is going to be equal to 100 grams because it's of the water. It's going to be multiplied by 4.18 because that's a specific capacity of water. I'm going to multiply that by, in this case, 10 degrees. Okay, we don't need to actually do that. And what I'm going to get here is 4.18 times 10 to the 3 joules. Now remember, depending on what the question asks for, if it asks for in terms of kilojoules, it would be 4.18 kilojoules, because 10 to the 3, which is 1,000, is represented by the K there. All right, so we want to do food. A simple way to do it using a calorimetry technique is to ignite a weighed sample of food, so we know how much food there is. We use it as a fuel to heat a particular volume of water and measure that increase. Now, that's very similar to, like you got here, a spirit burner setup. So let's go through a spirit burner, then we'll convert it to a food one. In the spirit burner, I'm heating some sort of fuel. It's heating the water here. There's got to be a temperature increase, and that's what I want to look at. So you're going to heat up a known amount of fuel to see what the energy content is. Now, if we're doing food, this part here becomes, that's my little cookie. I put my cookie there. I'm going to combust that. That's going to heat up the water, and we're going to measure the temperature increase. Potential issues of using this sort of setup is there's no insulation. It's a big issue with a setup like this. And what it means is when the energy is released, rather than going all into that water, the energy is going out here as well. And the problem with that is it means there's an underestimation. Estimation of the energy content of the sample. So, and because there's no insulation, that's what you want to try to insulate things. So all the energy that's being released from whatever you do in here goes into your water. But imagine we've done this, and we've done cookie A and cookie B, and we want to compare. The way we would do that is do the calculation we've done before up above, and then divide it by the mass of the food. Now, here's an example of that. I've got 1.78 grams of food with 50 grams of water. It goes from 20 to 59 degrees. So that's going to be an increase of, that's going to be an increase of 39 degrees. So how do I do that? I'll use this equation I've got there. Energy released per gram is going to be the mass of the water. So remember, mass of water, which is this bit here, 50 times 4.18 times, I said 39, and I divide that by 1.71 because I want it in terms of grams. That would give you 81518, wrong thing, 8151 grams. I don't need to actually write that there. Sorry, joules I meant. Divided by 1.71. If I want, I can convert that to kilojoules, which would be 8.15, 15 kilojoules divided by 1.71. So my answer is going to be 4.77. Now remember, it was kilojoules per gram. Now remember, I could write the kilojoules as joules and that would be in the thousands, but that's one way to do it. That's how you can do that sort of calculation. All right, so let's have a look at some other terms. So we've got some vocab terms here. So we're looking at solution calorimetry. So we're using heat exchangers in water in solution. So we can do different setups there. We're going to use a calorimeter, which is what measures out that heat change. The change in enthalpy is the amount of energy released or absorbed in the chemical reaction. When we talk about dissolution, if we talk about that, that's when we get solutes like a salt dissolved in a solvent to form a solution. Endothermic is a sort of chemical reaction where the energy is absorbed from the surroundings. And if we want to calibrate something, we're looking at adjusting the instrument using the standards. So the idea is, the example we used up here, you wouldn't really be able to calibrate it properly. The examples over here have been known not to always be calibrated, but I'd probably wanting to try as much as possible if I was using a system like these to calibrate them, just because it gives you better accuracy and better consistency. But these are just a couple of examples of a simple solution calorimeter. It's a bit better than the Spirit one we did before because there's some insulation. That's what we're talking about here. It's an insulated cup, insulated stopper. And you're doing that sort of thing. So you're insulating it to make sure that any changes in temperature are going to be, any release of energy or absorption of energy is going to be reflected in the temperature change. Okay. So that brings us into something called the calibration factor. This is the amount of energy required to change the contents of a calorimeter by 1 degree with these units. And the reason we want to do that is if we know what the calibration factor is, we can use that to get more accurate measurements. There's a way of doing that depending on your setup. You can use electrical one. So calibration of the calorimeter by supplying a known amount of electricity. That is this formula here. So we put the energy release would be the potential difference, so that the volts that are applied, the current that's used, and how long it's gone for. So we put that in, and then we'll get an idea of what the calibration factor is. And as it says here, the calibration allows for greater accuracy than just using the heat capacity of water alone. So it's giving you more consistent results. Because more importantly, it takes into account the heat absorbed by the entire inside of the calorimeter. So, even the best we could do, the thermometer will absorb some energy. The stirrer will absorb some energy. The lid will absorb some energy. Not much necessarily, but just a little bit. And so we can account for that. Then that's good. So here's an example of how we can use calibration factor. It's the energy released. That's that VIT. So the voltage, the amperage, the current, and the time. And we're going to divide that by whatever temperature change we see. Okay. So the calibration factor, so it's joules per degree centigrade. And what we want to look at here is what the final minus initial temperature is. So that's what we're after. So let's have a look. A solution calorimeter is filled with 100 mils of water. So 100 mils of water recorded at 19.5 degrees. We get a current of 2.52, voltage of 5.68. and the final temperature is that. So remember, our delta TC is going to equal final temperature 24.25 minus 19.5. That will give us 4.75. Oops. Sorry, let me restart again. That'll give us 4.75 degrees Celsius. The other part being, we want to calculate the energy. So the energy will be VIT. Voltage was 5.68. The amps was 2.52. And the time was, sorry, I missed that one, 2 minutes. So we want that in seconds. So that's going to be 120. That'll give us a value of 1.72 times 10 to the 3 joules. And now we're going to use this formula up here. So CF equals, let's just write this out again just so it's very clear. Delta TC, so that's going to be 1.72 times 10 to the 3 divided by 4.75, and that will give you an answer of 362 joules per degree temperature increase. Okay. Just remember something I noted before, and it's a useful little thing to remember here, is that these calculations are done in joules. So if any answer happens later on and it needs to be converted, you need to be able to convert to kilojoules or go from kilojoules back to joules. All right. So let's have a look. So we talked about electrical calibration. We can also do a chemical one. Using a combustion reaction with a known delta H. We've got an exothermic reaction. It's the opposite of endo, so it's describing a chemical reaction in which the energy is released into the surroundings. And nice little tip here, the heat of neutralization reactions will require Q to be calculated from the number of moles of the limiting reactant. That's what we need to keep in mind there. So what we've got about the heat of neutralization, this is a neutralization reaction. I'm not going to go into detail of that. You can see the net reaction is OH minus plus H plus, both aqueous, goes to liquid water. So we've got an example. A solution Cameruda was chemically calibrated using from dissolution of 5 grams of ammonium nitrate in 100 grams of water, held at 18 degrees Celsius. All right. The lowest temperature reached after dissolution was 14.5. So we know straight off the bat that we can get the delta T. So we can get the delta T from there, and that would be 14.5 minus 18. So that would be minus 3.5. Sorry, the computer's playing a bit weird. Minus 3.5 degrees Celsius. Okay, so just going to put that there to the side for a moment. We'll come back to that. All right, so what do we do next? First off, got to calculate the number of moles of ammonium nitrate in 5 grams. So that's, we're going to go N equals mass over molar mass. So the molar mass of ammonium nitrate is 80, and the mass we've told we've got 5 grams, and that's going to give you 0.0625 mole. Now we can look at calculate the number of kilojoules absorbed from dissolution. So we know delta H, so that's how much energy is released per mole. So that's why we've worked out the mole. So we can work out Q. Q is equal to number of mole times delta H. So that means the number of moles 0.0625 times 25.7, and that will give you 1.606 kilojoules. And now remember that would be 1.606 times 10 to the 3 joules, just to keep that in mind. We know what the calibration factor is. Okay, so let's should give myself more room here. We change color. Calibration factor is going to equal Q over delta T. Q, if you remember, was 1.606 times 10 to the 3. Divide that by 3.5. Got that before. That was this bit here. So we've got that difference there, and then that will give you an answer of 458 joules per degree Celsius. Now, keep in mind, just so a note, I did do negative there because that's what that would give you. But we're just looking for the temperature difference, so hence we can use, in this specific case, the fact that there's no negative here anymore, because we're looking for that energy difference, the temperature difference. All right. So the calibration, if we're looking at correct sig figs, the calibration factor would be 4.5. Be 4.6 times 10 to the 2 joules per degree Celsius. Okay. All right, so let's move back over here. I won't labour this point too much here. How to use a calorimeter. So it's important you actually remember this. We calibrate it first. We measure the masses or volumes of the chemicals that we're going to use. So we've got accurate values. Measure the temperature of the water or solutions. Add the solid or solution to the calorimeter, whichever happens to be. Record that temperature. You perform the calculations. If you need a delta H, especially for the example we gave before, use the appropriate sign in there. All right, so that's how you use a calorimeter. So just to reiterate, exothermic heat produced by the reaction is released into the solution. So that's what's going to heat up, results in an increase in temperature. Endothermic heat requires absorbed from the thermal energy of the solution, so it's absorbed from, which means there's a decrease in temperature. Just a note, most solution calorimetry is done in aqueous solutions, so water solutions, and that's where we can use the process we used above. Okay, and that's sort of what I've just talked about here. So in solution calorimetry, energy change is calculated using this equation, what we just talked about. Calibration factor times the change in temperature. And if we need the delta H, you can find the delta H by energy change per mole. All right. So depending on what the question is asking for, again, it could be eventually asking for that, and you're giving all the other information, and you've got to work your way back to that. All right. So this is definitely a good tip here. When you're writing it in your book, especially when it comes to SACs and exams, delta TC for calibration temperature change, and delta TR for reaction. It's useful to make a note of that so you don't forget. Yeah, and you got this part that's coming from the data book. Okay. So in this question we're going to go through here, one of the key things is we've already been provided with the calibration factor, which is always nice to have because we don't have to calculate that. So we can make a note and say that the calibration factor is 463 joules per degree centigrade. We can work out the energy change. So I'm just going to write E, and that's going to be CF times delta TR. So it's a reaction change in temperature, and that's what that difference is there. That's going to be, I think, 1.52. Oops, so I was sort of close. It should be 0.52. Don't know, I put the 1 in there for some reason. So it's going to be 463 times 0.52, and that would give us a value of 240.8 joules. So that's how much energy, in this case, there was energy change. So next step here is to work out the number of moles of sulfuric acid. So that's H2SO4. Remember, what we're calculating is the molar enthalpy. All right. So to do that, we need to know what the delta H is. This is delta H. So number of moles of things, that's going to be mass over molar mass, 0.231 over the molar mass of sulfuric acid, which is 98.1. That'll give us an answer of 2.35 times 10 to the negative 3 mole. Now our delta H, because remember delta H is basically energy divided by mole. So our energy we got here, I think I copied this down wrong, so I'm going to go over here, so let me correct this over. When I calculated that, don't know why I put 248, should be 240.8. So then when we do our delta H here, that's going to be 240.8 divided by 2.35 times 10 to the negative 3. So that means we're going to get a value of 1.02 times 10 to the 5 joules per mole, which we can represent that as 102 kilojoules per mole. So if you have to write the chemical equation, it would be H2SO4 as a liquid going to H2SO4 in aqueous solution. Don't know why I put the equals there. It's late, so that probably explains it. Delta H equals 102 kilojoules. Now I think strictly speaking it should be kilojoules per mole. I think Vika might be doing a little bit different, but strictly speaking it should be kilojoules per mole there. So let's have a look at this question. A solution calorimeter containing 100 ml of water was calibrated by passing 4 amps of current through the instrument for 35 seconds with a potential difference of 3 volts. Now, I'm going to do a couple of these things as I'm going, but keep in mind we're looking for to determine molar enthalpy change for this reaction here. All right. So what I'm doing here is calibration factor. So we have to calculate this one. It's a solution one where we've got that potential difference, and it's an electrical one. So I'm going to go VIT instead of voltage being, it was voltage 3 times 4 times 35, and that would give, and there was a, what was the temperature difference? Temperature rose by 0.7, so that's our temperature difference there. Sorry, I actually should have put something in there to be complete. Oops. Okay, so that would strictly, again. So that should be delta TC, and that should be, what was 0.7. Okay, that will give an answer of 600 joules per degree centigrade. That was what the calibration factor was. So the temperature rose by, so when 6.6 grams of calcium chloride hexahydrate, which is this one here, was added to the solution calorimeters and dissolved by rapid stirring, there was a decrease in temperature. So it's, even if you don't get to, when you're doing the answer, the temperature dropped, it means it's going to be endothermic. So you're going to have a positive mole enthalpy change. So that's endothermic there. Keep that in mind. It's a good way to check if your answer is correct. So we want to look at how much energy was, in this case, absorbed, to what the energy change was. So energy equals a calibration factor times delta T. That's a reaction. Don't know why I put an F there. So that's going to be what we had there, 600 times, now we were told what the temperature was, the temperature change was, is 0.895, and that gives us 537 joules. Now we want to calculate the energy per mole, because remember it's a molar enthalpy. So the mass of, normally I'd actually write the whole thing in, but that's going to take a bit of time. It's the mass of the calcium chloride. It's going to be, sorry, the number of moles would be mass over molar mass. So the mass we were given of that was 6.6 grams divided by a molar mass of 219.1. It's going to be equal to 0.0301 moles. So therefore, we want to get this value and this one and divide them. So our delta H now is basically E divided by N, E being, what was E? 537. Moles was 0.0301, and that's going to be equal to 17,819 joules. Because remember, enthalpy is done in kilojoules, we need to change that to 17.8 kilojoules. That should have been per mole. Oh, no, so this one will be per mole. So with this one. Okay, so delta H fully is going to be plus, remember, because it's exothermic, it's endothermic, 17.8 kilojoules per mole. And that would be our answer. Now, I was going to do this one, but I'm not going to do that now because the video is long enough as it is.